Hi, and welcome back to my channel Math Caffeine. This is the introduction to the series on congruent triangles where I will introduce you to all the theorems and corollaries that are needed for this series. Let's get started. The first theorem covered is called the triangle sum theorem. It states that the sum of the interior angles of a triangle equals to 180 degrees. In the image below, this theorem can be easily proved. For every point of the triangle, there exists exactly one line parallel to the opposite side. If one side of the triangle creates a transversal between these two parallel lines, then alternate interior angles are congruent. For example, angle 2 and angle 5 are congruent because they're alternate interior angles when this transversal cuts through these two parallel lines, and angle 1 and 4 are congruent if this transversal cuts through these two parallel lines. Angle 3, 4, and 5 create a line, so these three angles should add up to 180 degrees. Using substitution, we can see that angle 1, 2, and 3 equals to 180. Therefore, the degrees inside a triangle should equal to 180. The next theorem is about exterior angles. It states that the measure of an exterior angle is equal to the sum of the measures of the two non-adjacent interior angles. In this case, angle 4 is equal to angle 1 plus angle 2. This makes sense because angle 3 and 4 are a linear pair, and therefore must equal to 180 degrees. According to the triangle sum theorem, we know that the interior angles of a triangle equal to 180. So, angle 1 and angle 2 is equal to angle 4. Remember, a corollary is a statement that can be easily proven by a theorem. There is a corollary that goes with this theorem, which states that the acute angles of a right triangle are complementary. This also makes sense because if a right triangle has one angle that is 90 degrees, and the sum of the interior angles of a triangle is 180, then 180 minus 90 equals the sum of the other two angles, making them complementary, since those two angles should add up to 90 degrees. Theorem 5.3 is on the properties of triangle congruence. We have already looked at similar properties. These are just pertaining to triangles. So, to sum up, the reflexive property states that for any triangle ABC, it is congruent to itself. The symmetric property states that if triangle ABC is congruent to triangle DEF, then triangle DEF is also congruent to triangle ABC. The last one is the transitive property, where if triangle ABC is congruent to triangle DEF, and triangle DEF is congruent to triangle JKL, then triangle ABC is congruent to triangle JKL. Theorem 5.4 is the third angles theorem. If two angles of one triangle is congruent to two angles of another triangle, then their third angles must be congruent. For example, if angle A is congruent to angle D, and angle B is congruent to angle E, then angle C must be congruent to angle F. This does not state whether these two triangles are congruent or not. We only know that their angles are. The next theorem helps to prove if two triangles are congruent. It is the first of four we will learn. It is the SAS theorem, or side-angle-side theorem. If two sides and the included angle of one triangle are congruent to two sides and the included angle of a second triangle, then the two triangles are congruent. For example, if side AB is congruent to side DE, angle B is congruent to angle E, and a side BC is congruent to side EF, then these two triangles are congruent. The next theorem is about base angles theorems. If two sides of a triangle are congruent, then their angles opposite them are also congruent. There is a corollary that can be proved easily with this theorem, which states that if a triangle is equilateral, which means all three sides are the same, then it is also equiangular, which means that the angles are the same. The base angles theorem has a converse, which states the opposite, where if two angles are congruent, then their opposite sides must also be congruent. This one also has a corollary, which states that if a triangle is equiangular, meaning their angles are the same, then it is also equilateral, meaning their sides are the same. The next theorem states that if corresponding sides of two triangles are congruent, then the triangles itself are congruent to each other. For example, if side AB is congruent to DE, and side BC is congruent to side EF, and side AC is congruent to side DF, then these two triangles must be congruent. The next one pertains to only right triangles. It is the hypotenuse leg, or HL, congruence. If the hypotenuse and leg of a right triangle are congruent to the hypotenuse and a leg of a second right triangle, then the two triangles are congruent. So if this side is congruent to this side and the hypotenuse is congruent to the hypotenuse in this right triangle, then these two right triangles must be congruent. Remember, a hypotenuse only exists in a right triangle. It is the longest line of the triangle and is always opposite to the 90-degree angle. This makes sense because since the inside equals to 180 and one angle is already 90, there is no way that either of these angles can be greater than 90 or it will no longer be a triangle. This next theorem is going to help you prove congruency of two triangles and is called the angle-side angle, or ASA theorem. It states that if two angles and their included side are congruent and their corresponding angles and their included side in another triangle, then the two triangles are congruent. For example, if angle A is congruent to angle D, angle C is congruent to angle F, and side AC is congruent to side DF, then the triangles are congruent. The final theorem in this series is another theorem on proving two triangles are congruent. It is the AAS, or angle-angle-side theorem, which states that if two angles and one non-included side of the triangle is congruent to two angles and the corresponding non-included side of a second triangle, then the two triangles are congruent. For example, if angle A is congruent to angle D, angle C is congruent to angle F, and side CB is congruent to side FE, then these two triangles must be congruent. The most important thing to take away from this series and its many congruency theorems is to remember that order matters. For example, AAS, angle-angle-side, must be two angles and a side, not just any two angles and any side. This series will cover methods to use these theorems to prove congruency in triangles. Thanks for watching. As always, feel free to email me with any comments, questions, or concerns at mathcaffeine@gmail.com. Happy studying!